Okay, thanks friend for watching these videos, and I want to thanks actually to give me this opportunity to share my work. And as the title see that is liquid crystal biosensor chip, I will introduce you some liquid crystals technologies for biosensor applications and some of the work based on my lab, and I will give you some future work that I want to do in our futures. Okay. And my name is Yuchen Xiao. I come from Taipei Medical Universities and the Great Institute of Biomedical Optometrics. Okay, as you see that liquid crystal actually is a mesophase between the crystal and the liquids, and based on these properties, liquid crystals owns the both property of the crystals arrangements and the liquid crystals fluorescence properties, and the liquid crystals owns these two optical properties and can be do some interesting applications such as biosensors, or can be do some photonics devices. And based on these technologies, liquid crystal actually has been changed our humans' worlds, and we use the liquid crystals doing the TVs and computer or your smartphone monitors. Okay, the most commercials materials of the liquid crystal is the nematic phase and sematic phase, and also crystalline phase, and these three phase property of the liquid crystals owns their spatial optical properties. And in my lab, I also use these three parts to doing some biosensors applications. Okay. So what is a liquid crystal biosensor? You can see that it is liquid crystals will align in between the gold grid here, and this will get the alignment layer, and that alignment layer will make liquid crystals align to the same directions. However, we put some antibody here, or we put some ligand here. So if you detect waters on some spatial materials, and that material will get the interaction between the ligands, or if you are doing the biosensors, your antigen will interact with the antibodies, and that part will change the alignment layer, orientations of the liquid crystals, and make the liquid crystal get the different optical signals. You can see that if the will align here, the image will be dark. However, if you some goods or some material interact with the liquid crystal interface, we will make the liquid crystal devices in the dark, in the brightness signals. However, based on these two signals, we can easily to quantize that the concentration of the materials, or the concentration of the goods interact with the liquid crystals materials. So for liquid crystal biosensors, there are two major parts. One is the cell devices. We do in these sandwich device structures. We prepare the clean glass slide, and the DNYP alignment layer coat here, and put the CA125 mouse antibody here, and we made the immunodetections with the CA125 antigens to interact and form the immunopaired and put the glass here, assemble the liquid crystal cell, put liquid crystal material in, inject here, and the different concentration of the immuno pair or biomolecules over your goods will change the directions of the liquid crystal here. So another is a TEM grade, because the liquid crystal owns the property of the four properties. So the liquid crystal will flow anywhere. If you didn't keep some confinement here, the liquid crystal will flow, and it is very hard for the commercial application. So we put liquid crystal inside the TEM grade here, and you can see this is a liquid crystal here, and the goods detections that with the liquid crystal interface here. We change the colors here. So this is a two major part of liquid crystals, biosensor or sensors applications. And this is our previous word. It is a different concentration of anti-CA125 antibodies, different concentrations, and interact with the CA125 cancer biomarkers here. And you can see that the different concentration between the immuno pairs, we can get a different brightness of the liquid crystal images. As you see that if you use 0.1 anti-BSA, anti-CA125, and interact with the 10 microgram per milliliters CA125 cancer biomarker, will give the brightness, the lightness. So if your blood or your owns the 10 micrograms per milliliters cancer biomarker, you will give the brightness figures in your devices. Okay. So this is our new world. We're using the three major material. One of that is the crystalline liquid crystal, and doing the vertically crystalline crystal biosensors devices. You can see this is the structures. If you interface up between the DNOAP and the liquid crystals, will change the directions of the crystalline liquid crystals. Will make it transfer from this is the focal conic state, means that the random scattering directions of the liquid crystals change to the planar state. This planar state, and make the liquid crystals color change. So as you see, this figure is a 10 nanogram per milliliters, and is a 0 femtogram per milliliters. And you can see that the different concentrations of the BSA, you give the different type of the colors, and you change your devices from red to green and to blue and to purples. And that is because the bright reflections from the crystalline liquid crystal was changed, and different change of bright reflections will reflect different colors, and will make your devices to reflect the different colors, and to contrast the biomolecule from crystalline liquid crystal biosensors. And you can see from these figures, you can observe that there is a different concentration here. You increase your concentration, your transmitters will increases. And if you decrease the concentration, your bandwidth will decreases. So based on that, we advance the devices to using the single vertically crystalline liquid crystal biosensors. You can see that we just only use one alignment layer here, and put the biomolecule here, and put the crystalline crystal here, change the crystalline crystal from focal conics to the planar here. Okay, so it's the same mechanism. You change the directions of the crystalline crystal, you change the reflectance. Okay, you can see that it's a different color from 0 to 1 microgram here, and this cross polarizes optical microscopy images. You can observe that it's got many different line here, and if you increase your biomolecular concentrations, we will make the different light decreases here. So these are figures, the same behavior. Increase the concentrations, increase the transmittance. Decrease the concentrations, increase the concentration, your bandwidth will decrease. However, the most important is that the single vertical substrates used in this research, you get the linear behavior here, which made the crystal biosensor more potential for commercialize in the futures. And we try to make the devices more stable, so we put the polymers and inside the devices and to stabilize the crystal biosensor here. And because we put the polymers, so we made the devices was more thin, like a fin, and that fin was inside these devices, and we can use our smartphone to detect the signals. So these devices is 0 and 10 microgram, and is imaging from our smartphone's cameras. And based on these images, we can use the software to quantize the images and get the data here. Is the intensity, is the concentration. If you increases the concentrations, your intensity was increases here. So based on these figures, we can make these devices more powerful for commercializing futures. And it is transmittance spectrum here. Another application was used in the microfluidic liquid crystal biosensors. We put liquid crystals in these multi-channels microfluidic devices, and we can quantize each channel's brightness. You can see that this 0 microgram is 1 microgram, and it is in cross polarizer and it is in parallel polarizers. So we can observe that inside the microchannels, liquid crystal can well align inside the channel and to detect the biomolecular concentrations. So we also doing the figure that these intensities and this concentration of BSA in log form, and you can observe that this increase the BSA concentrations, its intensity was increases. Also, we also doing some immune detections behavior here, and it got the same optical behavior. So based on this research, liquid crystal can be applied for these microfluidic applications. Okay, and these different flow rates inside the channel. You can observe that if your flow rate was too high, it is hard for liquid crystal to align well inside the channel. So we consider the flow rates here, and observe that the best flow rate was 10 microliter per minute, and for these microfluidic liquid crystal biosensors. And also we try to commercial the liquid crystal biosensors. It's our design products, design charts here, and we also made the liquid crystal chip inside the box and read out the signal in your smartphone, and that is our futures work. Okay. Another important is the dye-liquid crystal biosensors, and that is because the dye-liquid crystal biosensor can make liquid crystal biosensors got a higher sensitivity and made the manufacturer's raise lower its cost, and increases the more potential for commercialize. Okay, we can observe that this dye contents here is a chemical structure here, and is 10 little microgram per milliliter is 1 microgram per milliliter PSA concentration. You can observe that if you increase your concentration, your color will be more increased here, and that is the skin flow views of the dye liquid crystal biosensors. And we clean the substrates and the DNOAPs, lobbies, and mobilizations of the BSA and antigens, and in that with the antigens and assembly the LC cells. Okay, also put this. We can also put these singly devices inside the structures and put the smartphone here to detect the colors, and use the software to computalize the images and to observe that and quantize the BSS concentrations. Another important part is the paper-based dye liquid crystal biosensors. And in the previous our work, we always use the glasses or plastic film. However, in this part, we try to use the paper to doing this liquid crystal biosensor treat. You can see that it's a paper-based microfluidic chain here, and it's 0 gram, and it's 10 microgram per milliliters BSS concentration. You can observe that the different color here is darkness, is brightness, and it is observed from our smartphone here. And we also can observe that the different color images. So our future will try to combine with liquid crystal biosensors and microfluidics, and also we try to use the OLED flat light source to make the devices, and try to use the liquid crystal devices as a commercial devices, and finally we will read out the data and to try to set up data, there's a big data to make our scientists or our customer too easy to use the data to identify your maybe your disease, or you want to try to analyze the BSS or something cancer biomarkers concentrations. So that is our lab's work focus on these liquid crystal biosensors. Okay, thanks for your attention, and thanks for you watching this video.